So guys, hello everyone. Can you hear me?
Yes, we can.
Okay, nice. So today is the last lecture, and today we will speak a little bit about such concept that's called optomechanics. So today's lecture will be like a small, short introduction to optomechanics. I think it won't be very long, and also I will discuss a little bit about what we will have next. So optomechanics. I have a question for you. Imagine the following structure. Uh, Imagine that you have some road with two like with two cylinders, one and two. And this road is, well, it's attached to something like here, but the most important thing is that it can rotate. It can freely rotate around its axis. And one of the cylindrical objects is perfect absorber. So it absorbs all the incoming light, like all the incoming light. One is perfect absorber. Second one is perfect mirror. And what happens, I take two sources of light and I shine the light on the perfect absorber. I shine some light on perfect absorber and shine some light on the perfect mirror.
It's some kind of.
Sorry, can you please repeat?
No.
I don't think that I get it. Can you repeat this?
No, I'm sorry, I just forgot to turn up my microphone.
Okay. So, how do you think? What will happen when I will shine the light on this structure?
I think there should be some kind of light pressure, like when we talk about perfect absorber, it's going to absorb the light and change its impulse. Но, like not impulse, it's импульс, момент, получается, правильно будет назвать. Ну, то есть поглощение получается поглощение энергии. It will be change the impulse of the light. If we're going to count it as, for example, photons, and mirror would be some kind of... Как будет абсолютно упругая? Elastic, yes, elastic reflection. So we could write the laws of the impulse conservation, impulse and energy conservation for the photons, and there should be some kind of rotation, I think.
Yeah, it's true. We know that photons actually have some momentum. So, well, like in a simple word, it's something like this. Also, you can calculate momentum. You can calculate momentum of light using the vector pointing, because vector pointing is like the flow. So it's like the momentum of light is also proportional to an average vector pointing. It's equals to 1 over c or c squared, if I'm correct, if I remember correctly. And because photons have some momentum, the perfect absorber, it will absorb like absorb all photons, which means that change of momentum of absorber equals to absorb momentum of photons. And the perfect mirror reflects all photons, which basically means that it changed this mirror changes momentum of photons from p to minus p. So the change of momentum of the mirror equals to momentum of photons. It's like it's a bit of hand waving, but I think I hope this is clear. So we have like change of change of momentum equal to p, and change of momentum equal to 2p here. So because of this, because we have different momentum on each of the.
Excuse me, but yes, shouldn't we actually just integrate around the surface? Because when we have the incident plane, for example, yes, if we put the axis xy, for y in this picture we have the normal incidence, but our plane wave in the all points of our spheres has the different angles. So shouldn't we?
It's not a sphere. Maybe let me find an image.
It's circle, like disc.
Yes. It's something like this.
Yes, okay, I understand.
Something like this. So it's just I don't know, some disc, something like this. Yes, and we will see the rotation. And actually, this is exactly what was observed by Petr Lebedev. This experiment that he has done in 1901. But actually, this is not the first time when people speak about the experiment of Lebedev. Was not the first time when people noticed that light has some pressure, that light acts on a matter in some way. The first one was actually made in 1619 by Johannes Kepler. It's 1 p.m. I think. And what he actually noticed that when the comet flies around the sun, for example, here we have the sun, and we have some trajectory like this, I don't know, something like this. And we have some comet flying here. Kepler noticed that the tail of the comet that the tail of the comet always pointing from the sun, in the direction from the sun. For example, it's something like this. So it's let's do this. This is the sun. This is the comet. This is tail of the comet. And this happens because sun has some flux of photons, some photon wind, if you will. And this flux of photons pushes on the tail of the comet, and this is why the tail of the comet is always pointing in the direction opposite to the sun. But first theoretical investigation of the pressure of light was actually made by Maxwell in 1873. It was made by Maxwell, where he introduced so-called, he wrote about, well, basically derived from Maxwell equations, he derived the basic equations for the light pressure. Well, and nowadays we actually have a lot of applications of quantum mechanics. The most famous is an optical tweezer, but I think I will speak about the applications in the end of the lecture. And actually, I would like to start with the following problem. We will consider just an infinite flat screen. Just an infinite flat screen. For example, it can be some piece of some medium, so it's infinite in x and y direction, and the axis is like this. And we have some plane wave incident on this piece of media with thickness z and permittivity epsilon. And the question is, what is the pressure of light on such medium? The first approach, like the most straightforward approach, is the following. We know that there is such thing as a Lorentz force. Lorentz force is force acting on charged particles by electromagnetic fields, and it's equal to charge of the particle times electric field plus 1 over c plus q over c velocity of the particle times magnetic field. But actually, when we have this is for the force acting on a charged particle. But when we have some medium. If you remember, we can see the media as a collection of charged particles, and we actually describe this media by some charge and current density, and we can actually introduce what's called Lorentz force density in the following way. It will be F small equal to charge density multiplied by the electric field plus 1 over C current density multiplied by the magnetic field. This is Lorentz force density. And obviously to get the total optical force, we need to integrate the force density over the whole volume of the object. And let's actually do this. So we can, and after this we can calculate the optical pressure. We can calculate an optical pressure just as force divided by the area. Actually, I think let me do the following geometry. It will be not like a rectangle. Let me consider the disk like in the experiment by the Piotr Lebedev. Let me consider the disk of some thickness. D. And we say that we do not account the boundary effects. Well, because the disk is finite, the boundary of the disk is finite, obviously, but we do not take into account the effects that are that happens due to this finiteness of the disk. So to calculate, and we want to calculate the pressure, this is like the z-axis, and we want to calculate the pressure of an incoming flight on this disk. So we can write the incident and magnetic field is E0, for example, EX exponent IKZ, and we also want to make another assumption that there is no reflection from the back plate, from the back part of this disk. So we write, just for simplicity, we write electromagnetic field inside the disk. We write it as E0 EX exponent to the IKZ. So we have some incident field, we have some reflected field. This is E0, this is E reflected, and we have some field inside the disk, which is just like a plane wave propagating in the forward direction. Well, this assumption that there is no reflection from this part, it's valid because we, in the end, will consider like I as a perfect absorber. Well, not perfect, but close to perfect absorber. And if thickness is much larger than the wavelength, then before light reaches this part, it almost perfectly absorbs. And another case is a perfect mirror, and obviously when everything reflects from this surface, then there is nothing to reflect from this part. Okay, and we also say that the radius is also much bigger than the wavelength. So we quote unquote consider this as an infinitely almost infinitely large cylinder, something like this. So let me once again write the expression for the Lorentz force. It's rho E plus 1 over C J times B. From Maxwell equations, we can write that B is just K divided by K0 times E, and thus it's equal to transmission coefficient for the field inside. It equals to transmission coefficient multiplied by the complex refractive index E0 EY exponent I A Z. Then we also need somehow find. Yes.
What's N? What
N is the refractive index of the disk, of the material of the disk. Then we also need to somehow find the density of charges and currents. The current density can be written as time of derivative of the polarization, which equals to minus I omega polarization multiplied by exponent minus I omega t. And the polarization equals to susceptibility multiplied by the electric field. So it equals to minus I omega t multiplied by the electric field inside exponent minus I omega t. Okay. And we also need to find the charge density, but I think that I'm assuming here that okay, I think that I'm assuming here that charge density is equals 0, because like we have some because all fields are transversal, they have like no longitudinal components. So we can write the expression for the no. I'm doing here the following thing. We are interested in the Z component of the force, of the optical force. And if you look closely at this part has only X component, because of electric field has only X component. So Z component of the force will be equal to 1 over C Z component of the current times magnetic field, which we can rewrite as follows. It will be minus I omega T divided by C electric field electric field multiplied by the magnetic field, and z component of this. But we actually need to calculate the time average quantity. And if you remember, if you have, for example, if you have pointed vector, which is c over 4 pi e of r and c times b h of r and c, then time average quantity of the pointed vector we calculate as c over 8 pi real part of e of r times h conjugated of r. So here we have f v of r and c equals to time average fz r. In this case will be equal to 1 over 2 real part of 1 over 2c real part of minus I omega key minus I omega key electric field multiplied by complex conjugated magnetic field, and we need to take only the component of this product. Once again, we have electric field equals to transmission coefficient E0 exponent I k z, and magnetic field we have transmission coefficient refractive index. It's also Ex here, exponent I k z. E0 Ey exponent I k z. So E times B conjugated will be equal to modulus of t squared modulus of E0 E z multiplied by the complex conjugation of the complex refractive index, and we will also have the following expression I k z minus I k conjugated z. And here we need to remember one very important thing, that because the refractive index is complex, it means that wave vector inside the media with n k0 is also complex. Well, from the physical point of view, it means that we have like oscillation part, which is real part of wave complex wave vector is responsible for the oscillation, and the imaginary part of wave vector is responsible for the decay. So basically, when we have imaginary part of refractive index, this basically means that we have losses in our medium. So in the end, this expression will give us the optical force, that component of the electromagnetic force, to be equal to 1 over 2 omega divided by c, square modulus of the transmission coefficient, square modulus of the amplitude of electromagnetic field, and the real part of minus I and conjugated chi multiplied by exponent to the minus k to prime minus 2k to prime, where k to prime is imaginary part of the wave vector, and we can rewrite this guy. We can rewrite this guy as k divided by 2 t squared e0 squared, and this guy can be written as imaginary part of susceptibility multiplied by complex conjugated refractive index exponent of the minus 2 k to prime z. Do you have some questions on this part? Okay. So we have the density of our electromagnetic force inside the medium. To find the total force, we need to integrate over the volume of the cylinder. So the total force, that component of the total force will be just integral from 0 to a, where a is the radius of the cylinder, integral from 0 to 2 pi, and integral over the height of the cylinder of the time average force density, rho d rho d phi d z. And if you substitute here the expression that we got, it will be something like this: k over 2 t squared e0 squared imaginary part of I and conjugated integral from 0 to a, integral from 0 to 2 pi, rho d phi multiplied by integral from 0 to d exponent minus 2 kz 2 primes z over d z. This guy is just surface of the cylinder, and this guy will give us just, if I'm not mistaken, it will give us 1 minus exponent to the minus 2 k squared d divided by 2k, not squared, 2k double prime. So in the end, our force is k over 4k double prime t squared e0 squared imaginary part of c and conjugated and multiplied by 1 minus exponent to 2k double prime d. But we can actually simplify this expression. We can actually simplify this expression a little bit. If you remember correctly, we actually assumed the first thing that we done is we assumed that the thickness is so big that because of the absorption inside the disk, the amplitude of electromagnetic field at this part of the disk is very small. Basically, it means that this guy almost equals to 0. This is the first thing that we do. We say that this guy equals to 0. Second thing that we do, we actually rewrite our electric susceptibility in the following way. We write that we know that electric susceptibility, that permittivity equals to 1 plus 4 pi t, which basically means that susceptibility equals to 1 divided by 4 pi epsilon minus 1, or in other words, 1 divided by 4 pi n squared, n prime squared minus n double prime squared minus 1 plus 2i n prime and double prime, where this guy is real part of refractive index and this guy is imaginary part of refractive index. Therefore, we can actually write that imaginary part of chi multiplied by n conjugated equals to 1 divided by 4 pi n prime squared minus n double prime squared minus 1 plus 2i n prime and double prime multiplied by n minus n prime minus n double prime. And I will keep like all the calculations, and I will just say that in the end, this thing equals to the following expression. In the end, this thing equals to the following expression. And also, we know that transmission coefficient equals to 1 plus reflection coefficient, which means that square modulus of the transmission coefficient will be equal to 1 plus reflection coefficient, also modulus squared. And in the end, our optical pressure will be equal to optical Z component.
I'm sorry, can you please not scroll the upper lines immediately, because it's hard to
okay, sorry.
the
I
pace.
can
Thank you.
If you want, I can speak lower a little bit.
No, the tempo is okay, but you scroll very fast the upper lines on the screen.
Okay. Maybe I can actually do it like this. Maybe to the better. Like this. Okay. So optical pressure is, of course, divided by the area. So this area will cancel out. And in the end, we will have K divided by.
Didn't you forget the area in the full formula of average F when you read F on Z axis?
Yeah. It's true. It's S here. Yes. Yeah. Also, I forgot to say one more thing. We have here like K over K double prime, but K double prime is basically K double prime here. Sorry, I also made a mistake. It's K0 here, and here it's also K0. It's because it's omega divided by c. K0 here. Yes. So it's K0 divided by K double prime. So it equals to K0 divided by N double prime K0. So it's just 1 divided by N double prime. And in the end, our pressure equals to F z average divided by the area of the cylinder. So the area cancels out. Then we have 1 divided by 4 and double prime. Then we have 1 plus r squared modulus of E0 squared. And we have an imaginary part which we write as n double prime divided by 4 pi multiplied by modulus of n squared plus 1. So this guy gives us 1, this guy also cancels out, and in the end we have E0 squared divided by 16 pi multiplied by 1 modulus of 1 plus reflection coefficient and everything squared, and multiplied by modulus of n squared plus 1. So this is our final answer. This is our final answer for the optical pressure on Lottie disk. So what we done here, we basically just took the expression for the Lorentz force, for the Lorentz force density, and integrated this expression over the whole volume of our scatter. But actually, this is not the only way to calculate optical pressure. And this is even not the most convenient way to calculate the optical pressure. For example, if somehow here we need to calculate an integral over the whole volume of the disk. So this was our disk. It's more or less simple in the case of the disk, but if you have some complex structure, we need to do several things. We need to find fields inside. We need to know fields inside our disk, and we need to integrate over the whole volume. But there is actually a second approach. And in this second approach, we can do it in much simple way. In the second approach, what we will need only the field at this boundary, only the field at the boundary of the disk. First, it's field at the surface, and second, the integral also should be done with the surface. And this can be done with the thing that's called Maxwell's test tensor. It's Maxwell's test tensor. what is Maxwell stress tensor basically? Maxwell stress tensor and Lorentz force are connected. Well, it's in some sense you can say that it's defined through the following expression. So Maxwell stress tensor is something like I think you can say that it's something like flux of the electromagnetic momentum, because we can write that the force is dp over dt. We can see that basically we have something like this, which is basically continuity equation for electromagnetic momentum. So this guy is electromagnetic momentum density, which basically means that this guy, which is called Maxwell stress tensor, and the physical meaning of this is electromagnetic momentum flux density. So, for example, if we have some structure and we have P1 incident and we have some P2 scattered, from the conservation of momentum, the momentum of this object, well, basically P1 minus P2. So this is why it's easier to use this guy, because we can just calculate the difference of this momentum. And the derivation of this Maxwell stress tensor is following. We actually start with the expression for the force density. We want to derive, right now we want to derive this expression for the Maxwell stress tensor, because force is the vector. This means that divergence of the Maxwell stress tensor is also vector. So the stress tensor is second rank tensor. Just important to keep this in mind. So let me then derive this expression. We start with expression for the Lorentz force equal to charge density multiplied by the electric field plus 1 over c, current density multiplied by the magnetic field. Right now, we're just doing everything. We're doing everything in vacuum. Just to keep things simple, we're doing everything in vacuum. For Maxwell equation, for Maxwell equations, we remember that for P rho is actually divergence of the electric field, and for P over C dot is actually curl of the magnetic field minus 1 over C times derivative of the electric field. So let me substitute these expressions here. Lorentz force density then will be equal to 1 over 4 pi divergence of E multiplied by E plus 1 over C over 4 pi curl of B multiplied by B minus 1 over C dE over dt multiplied by B. Up like this. So obviously this C and this C will be cancelled. The next thing that we do, we say that actually time derivative of the following expression E times B can be written in the following way, that it is dE over dt times B plus E times dB over dt. And dB over dt is actually, so it's C minus C times curl of E. So this expression in the end, this expression equals to dE over dt times B minus C curl of CE times curl of E. So we can rewrite the expression for the optical force or for the Lorentz force as follows. Lorentz force equals to 1 over 4 pi 1 over 4 pi divergence of E times E plus curl of B times B plus E times curl of P and minus, oh no, minus here, and minus 1 over C d over dt E times B. Then let me collect all the terms with electric and magnetic field at the same sides, and we can actually use one trick here. you see that here we have divergence of E, but let me rewrite this a little bit in the following way. Just rearrange everything. Just rearrange everything. It is clear that we have here like divergence of E, but we don't have divergence of B. We don't have such term. But we remember that divergence of B actually equals to 0. So what we can do, we can insert here something like divergence of B multiplied by B. We can just put it here because this term equals to 0. And if we do this, we'll actually arrive at symmetric version of this equation. In this case, the electromagnetic force will be equal to the divergence of E multiplied by E minus E times divergence curl of E plus divergence of E multiplied by B minus B times curl of the B, and minus 1 over C d over dt E times B. Something like this. And then we can rewrite this expression a little bit. If you remember, in the end, we need to arrive to the divergence of something, and this something will be our stress tensor. So we can use another vector identity here. The following expression 1 over 2 gradient of A times A equals to A times curl of A plus A times nabla applied to A. Here A times nabla applied to A is basically it's AI di applied to A. So it's something like this. And in the end, we will have the following expression. Force equals to 1 over 4 pi the divergence of E multiplied by E plus E times nabla multiplied by E plus divergence of B multiplied by B plus B times nabla multiplied by B and minus 1 over 2 right now I'm writing this part. I just wrote this part and I'm writing this part of like this expression. This is the gradient of e squared plus b squared. And also minus 1 over c, d over dt, e times b. So in the end, we'll need to also, we can look at this expression, we can look at this expression. Basically, this is like ei di of some scalar function, and we can write it as ei di delta ij of some scalar function, and basically this equals to divergence of identity tensor multiplied by this scalar function. So like the gradient of some scalar function is same as the divergence of the identity tensor and this scalar function. So we can rewrite this part. We can rewrite this part as 1 over 2 as 1 over 2 gradient of the like identity tensor multiplied by e squared plus b squared. And for this part, this is, let me use another color. This part. This is basically ei multiplied by dj ej plus ei multiplied by ej dj multiplied by ei. So basically this is you can write it as ei times ej. Write it as, sorry, give me 1 second. We can write it as e k times ej, and the product is ei of ei dk ej plus ej dk ei, and basically this equals to ek dk times ej times ei ej ei, and basically we can recognize this expression as divergence of the ei times ej ei ej. Guys, I understand that like last part can be a little bit complicated. So do you understand what I have just done? What I have just done? Like from the mathematical point of view, is it clear all this like tensorial operations, all this stuff? Or do you have some questions? Do I need to write everything, write something like in more details? Okay, so if no questions, then obviously we can do the same with magnetic field, and in the end we have Lorentz force equal to 1 over 4 pi equal to divergence of 1 over 4 pi E times E plus B times B minus 1 over minus identity tensor square modulus of E plus square modulus of B divided by 2. And we also have minus minus 1 over 4 pi C d over dt E times B. So we can actually see that this part is, if we multiply by and divide this part by C, we can rewrite this part as 1 over C squared C over dt d over dt over the t over 4 pi E times B, or on the other hand, d over dt of the Poynting vector divided by C squared, which is basically just time derivative of the electromagnetic momentum. And the final expression is following is divergence of the big guy, which I label as T, equals to dp over dt plus f. So this is like time derivative. This is change in electromagnetic momentum. This is force acting on particles, on charged particles. And this is flux density of electromagnetic momentum. Obviously, when we will like take the time average and we will time average everything, time average everything, you'll get the following expression. We will have no part with time derivative because it will be equal to 0 for the monochromatic field. So something like this, and this E once again equals to 1 over 4 pi.
Excuse me, the previous expression is for monochromatic, you said, yes?
No. This one is like for an arbitrary magnetic field. But well, when we will consider monochromatic fields, we will take the time average over the period.
Yes. I'm about the average F equals to the gradient of T, то есть like when you put away the average of dp dt, you mean that it monochromatic, yes? When we say the average dp.
Yes. We basically we consider. Let me write it. We say here that, for example, electric field of R and T equals to Q of R exponent to the minus I omega T, and we take the average over the period. Something like this. Well, it's basically as usual. Okay, so and expression for this T is once again 1 over 4 pi E times E plus B times B minus identity tensor E squared plus B squared divided by 2. And this guy is called Maxwell stress tensor. Something like this. And we will see now how much more simple it is to calculate an optical force using Maxwell stress tensor. Once again, I consider the same structure. This is just some cylinder with some effective index m. We have some incident wave. So the expression for the force, for the time average force, is integral over the whole volume of the time average force density, or integral over the whole volume of the divergence of the time average Maxwell stress tensor, or using the Stokes theorem, it is just integral over the boundary of this volume of just Maxwell stress tensor multiplied by the normal to the surface of this volume.
Isn't it ds? No.
So let me write it, draw it a little bit more quickly. So in our case, the normal to the surface is just Ez in our case, normal surface is just Ez, and on this part of the cylinder, electric field at the surface is just incident electric field plus reflected electric field here. For example, this is like Z equals to 0, just for simplicity. So also if you remember, we said that electric field at the backside equals to 0, and we don't consider the boundary effects here and here. So basically we can write the following thing. We can write that our Z component of the time averaged force equals to the Ez multiplied by T multiplied by Ez. It is sorry, it seems that yes, because we need to because our sorry, I made a mistake here. We need the outward pointing normal, which is minus Z, because Z is here. So it's minus Ez integrated over the surface on surface of the cylinder, and because our electromagnetic fields do not depend, we have like E on the function of V, and our field doesn't depend on X and Y coordinates. Basically, this means that the expression equals to minus an average.
Excuse me. Maybe I'm wrong, but you wrote the integral around dv after you use Stokes theorem. Shouldn't be here ds?
Just a notation for the.
I mean, in the average.
Yeah. It should be something like this. Yeah. And also multiplied by the surface of the cylinder. So you see, if previously we calculated like all these integrals, of course they're not very hard, but this is like the simple example. When we will have something more complicated, the volume integrals will also become more complicated. But in this case, we just need to calculate the X value of the Maxwell stress tensor. And we basically write that electric field, we can even write from the boundary condition that electric field at V equal to V0 minus, this is like before the cylinder, and after, this is like V0 minus and V0 plus are after the cylinder. V equals to V0 plus and equals to EX, for example, multiplied by transmission coefficient E0, and same for the magnetic field. Magnetic field at V equal to V0 minus, which is equal to Z equals to Z0 plus equals to EY transmission coefficient multiplied by complex refractive product of the media multiplied by E0. Basically, what I wrote here is just boundary conditions that field on the left part of the interface equal to the field on the right part of the interface. And on the left, we have incident and reflect part fields, and on the right, we have transmitted fields. So the will be equal to will be equal to 1 over 4 pi EV multiplied by EV, 1 over 8 pi, because it's time average, EV multiplied by EV conjugated plus BZ multiplied by BZ conjugated. It will also be a real part. And minus E squared plus B squared divided by 2. But we remember, well, this is basically E times E conjugated. Z is a part of this. But our electric field has no Z component, and our magnetic field has no Z component. So these guys, they're just 0. And in the end, we have something like 1 divided by 16 pi E squared plus modulus of the B squared or modulus of T squared modulus E0 squared divided by 16 pi and multiplied by 1 plus n squared modulus. Also, this minus here, this minus here. So if we put minus here, this will give us plus, plus, and plus. And finally, optical pressure is Z component of the time average force divided by the area, or minus TZZ divided by multiplied by area and divided by area, or in other ways, 1 plus R squared E0 squared divided by 16 pi and 1 plus n squared. And we can see that I will jump a little bit. This is basically the same expression, but we get it like in 2 lines. So something like this. Do you have any questions? So, okay, if no questions, then just like a couple of ways to use optomechanics. Well, as I told previously, the most popular way to use optical forces is optical tweezer. So basically, optical tweezer is just, well, in a simple word, if you have some laser beam, we have some gradient of the electric field here, of the electric field strength here, and if you put some particle here inside the laser beam, it will actually be trapped in the middle of this laser beam. And we can take the laser, and if we move this laser slowly enough, because of this potential which is created for this particle, we can actually move the particle. So you can think about this. I think I have image somewhere. image somewhere here. So you know this trick that if you have some airflow, you can put the particle inside this airflow and the particle will stay inside. And this is basically more or less equivalent image for the optical tweezers. And you can do a lot of different stuff with optical tweezers. For example, you can do something like this. You can take a lot of tweezers and you can create some images from atoms. This is basically each like shining point here is a single atom. Also, there are a lot of course, there are a lot of biomedical applications because you can manipulate these particles in a non-invasive way. For example, you can even manipulate some nanorobots. You can, let me maybe show you this image. So you have something like this. You have the structure with these two big like dots, which you put into two optical tweezers, and you have this like something like this. So it's like a propeller, I don't know how to call it. And you shine light here on this part, and it starts to rotate. And also you can make holographic displays. I think it will be impossible to show you the video right now, but if you want, you can just look at the supplemental material for these papers. So basically, here guys made the output of this work we made, and holographic display using optical tweezers. They were moving the particle with the tracking beam of an optical tweezer, and this creates this three-dimensional image. So something like this. Do you have any questions? So if no questions, there are also a couple of points that I would like to say. First one is that there will be an optional homework on optomechanics. I think the deadline will be like the same in 2 weeks, but once again, it will be optional. So it's like plus points above 100%. So if you want to get some additional points or something like this, you can do this optional homework, but there will be no resubmission. So you get what you get, because there will be like new year and exams, so you will have no time to do the corrections. Of course, like, sorry?
Could you please repeat what would be a deadline for this homework?
I will send you the homework with the deadline, I think today or tomorrow. You'll be able to find the deadline on the homework list.
Oh, okay, thank you.
So yeah, of course we will send you the feedback on this homework. but there will be like no resubmission for this homework, no corrections. But it's optional. So if you skip this homework, there will be no penalty for this. It's like additional points after the 100%. The second point is that on the next week, you will have homework corrections on 25th of December, and I think it will be offline, and time and room to be announced. But I think time will be like approximately 10 a.m. I think. And I think that's it until the new year at least. We will have the exam on the 13th of January, if I remember correctly, but I may be wrong. You need to double check this. And I think that today or maybe tomorrow, we will send you the exam questions. So something like this. Do you have some questions?
Yes, I have a question. So finally, would we have a possibility to use our handwritten conspect notes during the exam?
You will be able to use them, but only during the preparation.
Oh, okay.
So you will have some, for example, like, I don't know, 1 hour or like some time to prepare your answer to the question. And during this time, you can use. But when you go to defend what you wrote, there will be no possibility to use your notes. But when you write your answer, you can use them.
Yes, thank you.
Okay, so that's it. Thank you for today, and see you next week. Bye bye.